Okay. Now I request our student coordinator, Veda, to introduce our next speaker, Vishnu Vimjam garu.
I take the honor in introducing our next speaker, Dr. Vimjam. Dr. Vimjam has more than 15 years of experience in developing state-of-art EDA verification and sign-off tools as an architect and a technologist. Currently working as the Chief Product Officer at Real Intent Corporation, Dr. Vimjam applies his deep technical knowledge and expert understanding of customers' challenging verifications needs to drive product development for real intent world-class solutions for accelerating RTL sign-off, working with R&D and product management to design, build and test new products. Prior to Real Intent, he held consecutive summer internships at Intel Corporation. He holds a BTech degree from Jawaharlal Nehru Technological University and MS and PhD degrees in computer engineering from Virginia Polytechnical Technic Institute and State University. His research interests include SAT, BDD-based bounded model checking, and automatic test pattern generation algorithms. He holds 2 patents and has published several conference papers and online technical articles. Outside of work, he loves to travel and is an avid hiker. He is a proud student of Dr. Y. Padmasai ma'am and an alumni of our college, VNR VJIT. I welcome sir.
Hi, can you hear me all?
Yes, sir.
Let
We
me,
can hear you.
okay, let me share my screen. Okay, let me see, I can able to get it or not. Can you see my slide? First
Yes,
slide.
sir. Yes, sir. You can carry.
Okay, thank you so much for the invitation, Padmasai ma'am, and my dear friends and everyone at VNR. So happy to be sharing today with all the work we've been doing at the digital side, unlike the previous speaker who spoke about the analog side. Uh, my work has been, my research has been in ATPG solvers and formal verification. And in the industry, we've been working with something called static verification. So today we'll be focusing on that. I'm a chief product officer at Real Intent in Sunnyvale, California. I did my master's and PhD from Virginia Tech and bachelor's from VNR ECE department. Okay. Let's move on. So here is a brief outline of my talk. We'll talk about introduction, the verification challenge. We'll talk about shift left methodology, then some examples of how we solve various things in the digital world, followed by hierarchical flow and then a summary. So I will start by saying that, we live in amazing times. This is not my personal opinion, but it's a fact. You look everywhere around you, there is just so much computation going on. 5G, smartphones, Internet of Things, smartwatches, medical devices, big data, cloud, you name it, right? And then there is a advent of VR and AR, maybe in the next decade or so, and then AI/ML is already used in various applications, and finally we have self-driven automobiles and so on. So all of these are what put together is what we call the internet economy. Okay, the fact that I'm sitting at my home and able to give this speech, and all of you are able to listen from part of the world, is just amazing. And as a technologist, there's nothing to be proud of, more than proud of. So what is powering the internet is, of course, semiconductors. We all know that, and all teachers, students. There's a lot of future ahead of us, so we should be proud of what we have achieved and to be achieved in the future. If you look at the semiconductor revenue briefly, so in 2020 it was $465 billion. in 2021, we are now at almost 550, and 2022 was a little bit above 550, close to 600, right? And Intel used to be the biggest winner all through the years. I think in 21, Samsung took over, and you see the third position is held by SK Hynix. So the Koreans have advanced significantly in the semiconductor space. US still leads with other companies, Intel, Micron, Qualcomm, Nvidia, Broadcom, TI, and so on. Then we have MediaTek from Taiwan, which is has emerged in the past decade significantly again. Then we have AMD, Apple, Infineon from Europe, and Kioxia from Japan. A bunch of the Japanese semiconductors, for whatever reason, they have fallen behind, while the Koreans and Taiwans have, even Chinese are taking over. So as you see, the competition is very high, and because there is so much to be done, and the future is, with semiconductors. I just want to give a little bit overview of the growth opportunity we have here. So in 21, we have $590 billion, whereas in 2030, just 9 years from now or 8 years from now, it's going to be a $1 trillion industry. Just the semiconductor industry is 1 trillion. So imagine how many job opportunities that are there in this industry. And a majority of it is actually driven by three items. One is our personal computing and data storage. Every photo, video that you click, gets stored somewhere. Somebody is analyzing it. Somebody is, improving it. Google is behind improving it all, and so on. And then there is wireless communication, which, right now we have our handhelds. In the future, each car will talk to each other, and so on. Then we have automotive, right? Again, you look inside the car, it's all behind is electronics, sensors, like in the other talk, are everywhere around. Then industrial electronics, consumer, and so on. So we are looking at, annual growth rate of about 7%, and which means almost doubling in the next 9 years. I wanted to give this slide here. This is from Counterpoint. India, there's a lot of opportunity. So right now, the spending in India is about $300 billion, and it's growing at 19%. Okay, the sad part though is only 9% of it is actually coming from India, locally sourced, as you can see here on the right side. And it is expected to grow in 2026 only 17%. So we still have a lot of ways to go in India, and hopefully Apple setting up shop and so on will give a big boost to the Indian market, and eventually start to export this, because in the next 2 decades we are not going to see any slowdown in the semiconductor market. I want to give this view to see how complicated things have become, or how we're able to solve them. So the first slide on the top is from Apple in their A10 Bionic chips and so on, which they have started. If you look at a few years back, the chip had 3 billion transistors. Okay, when I was studying, 100 million was a big deal. So now we are at 3 billion, right? Just within a matter of 5 years or 6 years, A16 Bionic, next one, is going to be 18 billion transistors. 18 billion transistors on just something of a square inch chip. Imagine the complexity, all the breakthroughs that have gotten in there, and how much work has happened. Bottom two are a couple of things I bought from TSMC for the roadmap. So, we started N7, back in 2017 and so on. And the projected is N2, which is 2 nanometers by 2025. Moore's law was supposed to be slowing down, which it did, because Moore's law, every 1.5 years, your chip is going to double in size and the speed will double. For the longest time, it did. There were several problems in manufacturing that was faced. Still, Moore's law holds true. So, for example, in this case, in about matter of 7 years, we went up by 2 to 3x, which is still significant, because we are solving the problem through other means. Okay, and the highest end technology node maps, like 3 nanometer, 2 nanometer, are used in the high-end devices, premium mobile, data center, AI, and so on, while the mainstream ones will be used in the low-end mobile, networking, consumer electronics, and so on. So there's a lot of things going on in the background which we don't see in the manufacturing side. Okay. So what led to all of these, uh, things possible in the background, right? So there are three things that come to mind. First, we have the hardware design. Again, I'm speaking from the digital background. So when I say hardware design, it's more logic processing and everything that goes around it. If everybody starts to design something by themselves, okay, there is no togetherness, there is no standardization, right? So as the confluence happens with the standardization, things become faster. One team each understands each team better, and so on. So the standardization protocols, superscalar multi-core architectures, low power designs, and custom processing units like GPUs, TPUs, and all have boosted the design space of hardware significantly. Okay. Then we talk about manufacturing. Moore's law held for a long time. Then the transistor designs itself advanced, like FinFET. Now we have something called gate all around, and then there's a high K metal gate. There's so many advances there. And obviously, we want the state-of-the-art test equipment to be able to validate the chips that are getting out, right? Without being able to test them, you can't bring it out to the market. Then what we have in the background is the software advancements that are happening, which you don't see. And the first one is we are able to describe your design in higher levels of abstraction using like system Verilog, system C, C++, even these days, some people have started. So all of these let you to, human capacity will reach a certain point. After that, the machines have to take over. So abstraction becomes a significant improvement in every aspect of design. Then EDA toolchain has continuously scaled up. Okay, if you don't have the tools that are working to let you design and eventually manufacture, then you can't progress on it. Which then leads to the advancements that we need in verification and test technologies. So when we say verification, typically we talk about before manufacturing. When we say test, we talk about after manufacturing. And but to be able to test, you still need algorithms and the methodologies at the time, before you manufacture. So here is a modern ASIC/SoC flow. SoC is a system on a chip. So any design house, you start off with a standard functional components, like FIFO, for example, or shift registers or a register array. And these standard functional components are sort of a library that every design house has. Then you form an IP. Sometimes IPs are actually borrowed from third-party vendors in terms of a soft IP or a firm IP or a hard IP. Then you have the IPs become blocks. Then the blocks are built into something called chiplet or a mega block or a super block. Then we have an SoC, which is the full chip itself. Okay. And on the right side, we have here a typical ASIC design flow where you start with a system specification with a microarchitecture in mind. Then you start to build your RTL. Your RTL development takes a lot of time to be able to understand, verify, and so on. Then you integrate them into SoC, then synthesis, layout, and eventually going into fabrication. As you see, there is a lot of moving parts here. If you want to bring a chip out in 2 years, you have to start today. You can't start next year. You have to start today and plan. How are you going to get all the IPs from? Apple has to get their iPhone 15 next year. They have planned it 3 years ahead of time, right? So that's how complicated this process is. Which brings us to the verification challenge. So what are we talking about? There are 16 billion transistors on the chip in the next Apple version. So how are they all getting verified, ahead of time to make sure there is no bug in the logic, or memory or anything like that, right? So it's a 4-dimensional problem. Obviously, the first one is the size and complexity are ever increasing, and it's we already see day in and day out at my company that chips are, in a matter of 3 years, they're doubling in size. So that's a fact. RTL development keeps varying with each version. So it's not the same. RTL is like a software, right? So you keep developing your design in a software form, and that software is changing. And on top of it, it's not one person software. It is design house is importing, these IPs from several different IP vendors. And each IP vendor may be using a different EDA tool for their verification or a different verification methodology altogether. So there is no interoperability standard between the EDA tools. So it becomes very important if you're a design house trying to get a chip out to make sure your verification methodology gets right and be able to deliver in the time that you want it. I mean, if you want to take 5 years from now and deliver it, yeah, that's fine. But no, your requirement is to deliver it next year, not 5 years from now. So the challenge here is, any one critical bug miss, okay, will have a problem with your silicon. And if a silicon fails, silicon is not like software, it's a hardware. One bug miss, it'll cost you millions of dollars. And a lot of time is wasted in the process. So here is a simple example. When you're at the early RTL stage, okay, if you have a problem, let's say, it takes you a day to fix it. But if you go to final RTL stage, it takes like 10x the amount of effort. And if you have the same problem in a post-synthesis where actually your netlist level, you no longer have access to the RTL, you're dealing with the netlist, then you have to do ECO and stuff. Then you're looking at 100x complication. And if it goes after place and route and layout stage, then it's even more, right? And then if it actually escapes the silicon, finding that bug becomes really a nightmare. Sometimes people spend weeks and weeks of effort to find that. Okay, and if it gets shipped to your customer, then it's a big chaos, right? So the shift left verification is key to get things right. This phenomenon rather started, let's say, in the past decade, and it's ever increasing as we speak, and it continues to increase. There's no way around it. We can't go back to the old days. So what do we have in the established methodologies? Okay, we all know about simulation, where you write a test bench and then you check your design against the test bench to make sure you get expected results. It's a pretty complicated, time-consuming task because you have to know your design and you have to write all these complicated test benches. You can make actually bugs in the test bench itself, right? But at the end of the day, it works and it scales well. It provides very good coverage, 90-95% with a reasonable effort. Okay. And then at the system level, people started using FPGA prototyping and emulation because you are really verifying something before the actual manufacturing process happens, right? So in 1994, there was a famous Intel Pentium processor floating point bug, which escaped all of this. And then Intel lost like $500 million. And they started saying, we have to do a better job in verification. And that's when they started formal verification as a problem, as a means to mathematically prove a design for 100% correctness. Okay, it's a NP complete problem because it works in state space. It goes into state space explosion. So it works very well for smaller blocks, but when you go into millions of state elements and so on, then formal verification has a big runs into a problem. So assertions and covers, some of you may be familiar here through system Verilog assertions, are specific design properties that you write into the RTL. For example, FIFO send receive happens, there's no data loss corruption, or there's a cache coherency and bus protocols and so on. Everything that you know about your design or it should do, you can write into a SVA, right? And then you can throw it into a simulator, you can throw it into a formal tool and say, verify it for me, okay? That's one aspect that's going on. And then formal, thankfully, also gave us logical equivalency checking, because as you go into your ASIC design phases, design keeps transforming from one to another. So you want to make sure that the previous version of the design is equivalent to the current version of the design and to the next one and so on. So basically, you're not introducing new design bugs as you go through various optimization phases. So what we have here is a simulation again on the top, where the analysis finishes in a practical amount of time. However, not all failures are found with simulation. Why? Because it's only as good as your test bench is. If your test bench is not covering all the expected behavior of your chip, then it's not going to, simulation is going to give you all the failures. Whereas formal, it finds really deep bugs, okay, which cannot be found in simulation. I mean, which can be found in simulation, but it's not practical to think of it. The challenge with formal is it cannot find all the bugs because it's a very high complexity problem. It's a NP complete problem, right? So, and formal, unfortunately, also requires very big expertise in design itself, and of course, you need to have like a formal knowledge of like PhD level candidates sitting around and analyzing the design and trying to write the proper abstraction mechanisms for it to solve. We have on the right side is the new emergence, which is what we call static sign-off. As you can see, I put the arrow a little bit longer on the static side because it's able to solve problems that are not amenable to a simulation or formal. The good part about static, why it got successful, is it finds 100% of the targets. So if you give it a problem to solve and define what the problem is, okay, it'll solve it. You don't need to do anything about it. So it's a fully automatic. Of course, there can be a little bit noise here and there. We'll talk about that in a little bit. But static has really, pushed the envelope of verification. So what is static sign-off? Traditionally, we have a couple of items. For example, static timing analysis, which some of you may be familiar with. Static timing analysis deals with setup and hold checks after the netlist is run. So if you have two flip-flops talking to each other, you need to make sure the path between them, do not violate timing, right? And similarly, when you after place and route, you do layout, then you have a lot of design rule checks to make sure, blocks are not close to each other. There is no, signal noise interference and so on and so forth. However, it was not used until, let's say last decade, to bring it into a formal verification and simulation and structural, all things put together into the static sign-off space. The key here is minimal user intervention, okay? If you start to ask the user, hey, do I want to do this? Can you set it up this way? Can you write assertions of properties? You will never be, able to verify the chips that you do today. So static has become the de facto standard for several problem classes now. And I have listed a few here, CDC, RDC, low power, XProp, linting, DFT, and so on. And I can tell you for a fact that, there are a lot more problem classes that we're working on. And in the next decade, it may even surpass formal and other methodologies, okay? So how does the full tool flow work? It's very simple, right? You take the design, and the design is either you have an RTL, a Liberty, or a UPF, which is a universal power standard. And then you take some constraints from the user. How is your design operating? It's not specific to the properties of the design, but just like, for example, what are your clocks? What are your resets, right? What are your synchronizers? And those kind of information you take. And the tools automatically analyzes, just using these two information. The user does not give anything else to the tool. And it tries to identify 100% of the targets, right? That's the cool part about static is. So what we spit out is a setup problem. So a setup means something is wrong. Hey, you have 10 clocks in your design. Maybe you gave only 9. One clock is missing, right? You need to go and specify that clock to us so that we can verify 100% of your design. So when you reach into a setup problem, typically you go back and 90% of the time you fix your constraints and you rerun. We also occasionally see 10% of the time you actually find a bug in the design itself, okay, through the setup, which is actually pretty interesting because the user did not do anything. They just found a bug in the design, okay, nothing at all. On the other hand, the design violations, which we find out, are really important. And 70% of the time, we find bugs in the design. It could be RTL, it could be in a specification from low power, it could be some third-party IP, whatever it is, we find problem 70% of the times. 30% of the times, it does happen that there's a bad constraint that the user provided, so you got to go and fix the constraint. So this is very important here. One challenge continues to be that, debugging of what is the root cause, where is the fix? Is it in the design? If so, which part of the design, is non-trivial? Which part of the constraint is non-trivial? So that is where a lot of work and research is going on. So let's talk about a few things, where static is able to solve much better than, other techniques. So first one comes to mind is RTL linting, right? So linting is like, how do you compile your RTL, just like how you compile your C++ code, right? And be able to make meaningful results, okay, out of that, and help the designer in finding quick bugs, even though they don't do any test bench analysis. So this is where the key is. And it scales up very well to full chip level. It can go to like 5 billion transistor chip just like that in a few hours. No problem, it gives you. Modern linters have like 600 plus rules for various levels. And capturing any of these rules or even a subset of these rules is impractical for alternate mechanisms, okay? Although the challenge in a linter is, it can be noisy because it finds you 10 bugs. Maybe, 5 bugs are real and the other 5 is just noise and you have to get around ways. So these where the smartness in the tool comes in. I wanted to give a quick example of a combo loop here. A is assigned to foo is assigned to C, and then C is assigned back to A. If you look here, it's a simple example, and any hardware designer can look at it at the RTL and say, oh, there's a bug here, and they can fix it very easily. Now I make it a little complicated, and foo and C are in one module, whereas the C is actually assigned in a different module. Now you got to scratch a little bit. Well, did I make a mistake? What is the mistake here, right? I don't know, and you can't go to ask a simulator about this question. Is there a bug in my design? So these are the cases, for example, where lint of your RTL makes extremely productive task, and you don't have to manually review your RTL after every revision. Okay. Having said that, okay, lint, like I said, if it has like 500 rules, if you apply it on your full chip, it'll give you millions and millions of violations, and you'll never be able to verify it. So there's always a methodology that comes in practice that you have to do. So when you are at the IP stage, you identify a set of rules that you have to verify, and the designer have to clean it out. Then you go into the block level phase. You have to, for example, FSM integrity checks, or you have a complexity issues. You have to fix those. Then you talk about style. Make sure various design teams in your unit are adhering to the same style, because one person may leave the company and somebody else has to go and fix the problem, right? And more checks comes when you do the RTL integration and netlist and so on. So by having a phased verification approach in linting, you actually make it very practical. And these days, it's easy to say a majority of the trivial or gross bugs are identified in linting itself. You don't even need to go to the higher level solvers. So then let's talk about something called autoformal. So this is a class of design rules which are built on top of lint rules. Okay, but it's not just lint. It's actually does Boolean analysis through formal verification, and it's fully automatic. Okay, it works great for small IPs, but it may not scale for bigger chips because the number of checks are very high, and obviously formal runs into a problem. I listed here a few check examples, that you can actually work with autoformal. Any of these examples, okay, if you want to do with alternative verification methods, it is impractical because you have like millions of these checks around in your chip, and if you start to write assertions or monitors or coverage statements in simulation or test bench, you will not be able to reach, even the simulation may not finish. So it's important for autoformal to be able to be applied. It needs to classify something into a reachable state or unreachable state for effective usage. So I'll give a few failures to speak what I'm saying. Okay. So let's take a look at these 4 things here. On the left here, we have assigned foo equal to A and B, and bar is not A or not B. So clearly, foo and bar are inversion of each other. And somebody wrote, if foo and bar, then there is then the assignment. But foo and bar will always be evaluated to false here. Okay. So the if condition will never actually trigger in simulation, and synthesis tool will optimize it away. So the question is, did the user intentionally did this, or was there a typo? And foo and bar should have been some other expression, or even some other variables, right? They have to review this. Similarly, let's look at FSM state deadlock here on the right side. A simple example, it's of 2-bit FSM 0 to 00 through 11, and there is a self loop around state 10, right? So once you enter the state 10, the FSM will never go out of it. If you are in an automobile driving on a road and it goes into a deadlock state, imagine what will happen. So that's pretty bad, right? So you want the very critical things to be avoided as much as possible and automatically. Similarly, we have FSM unreachable state. So for example, here, 1, okay, is not reachable because there is no assignment to 1 from any state. 0 0 0 1 1 0 are reachable, but 1 is not reachable. So if it is not reachable, why did you code it in your RTL? Did you make a mistake, or did you want to synthesis tool to optimize it out? In which case you have to write a synthesis pragma, right? In which case, why did you actually write the default? Because default you have a XX, right? Which means your finite state machine is going to unknown state, which is really dangerous. Thankfully, in this case, they specified all the 4 states here, so default is never possible. So there's actually a pass here, whereas a 1 is an unreachable state, so it's a fail. Similarly, on the bottom here, we have something called out of range. Okay, you have 2 variables, index 2 down to 0 and 3 down to 0, so max values are 7 and 15. And you have a register 5 down to 0, where max index is going from 0 to 5, right? But you're doing something like q of index 1 plus index 2 equal to 0. Well, guess what? Index 1 and index 2 may go outside the range of q. Simulator will happily assign it to x or don't care it. Synthesis tool will happily, optimize it out. What will happen to your code? Did you really intend it to be that way? Okay. So there are various classes of problems which we are actually identifying through order formal without any user intervention. Along the way, we also have something called resetability and exprop issues. So what is it? In a modern design, there is various kinds of resets. Okay, there are power on resets, warm resets, cold resets, and then there's software resets. There's a configuration resets, and so on. Why are resets needed? Obviously, you want to bring the design into a known state before you actually start any operation, right? If you power up your chip, the logic there will go into some random state, unless it's a memory there which knows what it's doing. All the logic inside the sequential elements, flops, latches, and your memory registers, they will go into unknown state. So you don't want to do that. So that's why you reset them. But reset routing is very expensive because reset go into in every sequential element. It's not happening. So designers try to smartly avoid some resets. As a consequence, you run into uninitialized sequential elements. Okay. Sometimes the reset may be blocked from actually resetting the flop, or maybe the reset is not long enough that some flops downstream are not reset. So you will run into these kind of problems. Again, this is perfectly suited for static sign-off, and you don't need to specify anything to the user. And similarly, there is something called excess in the design. So this is not something you know about in the academia, but this is a real problem in the world. So when you are doing synthesis and simulation, simulation is working purely at the software level. Synthesis is purely working at the hardware level. At the hardware level, there is no such thing as a X, right? Everything becomes a 0 or 1 eventually. So how do you know there is what you're simulating for verification is actually what you get in your hardware, right? So you need to avoid all the X sources and sources of X optimism and pessimism in the design. And you can only do this with static verification. Now we have an interesting class. This is my favorite, which is clock domain crossings. I've been working on it for a while. And what is the problem? The problem here is that you cannot time paths between two asynchronous clocks. So here is a clock 1 on the left side and clock 2 on the right side. The elements are driven by each clocks, and clock 1 and clock 2 come from two different oscillators. Okay, phase lock loops. So they have no correlation to each other. Anyone can come at any time. So how do you make sure then the data that you're sending actually gets reliably captured into the receiving domain? You can't do that, and you cannot do static timing analysis on it because they are asynchronous. So this is a very common problem, and in fact, this is actually the kickstart of full static methodology, because one path that you miss in verification will toast your silicon, right? So you have to make sure every single CDC path in your design is actually protected. And one way to protect here is what I have a picture here. This is called a CDC handshake, where you have a control signal which sends sort of a pulse into the receiving domain, which is a synchronizer here. And the synchronizer is in initially off state. And then when it goes to the on state, that's when it is ready to take the data. And once the data is received, then there's a feedback which goes into, again, the transmit domain to tell the control that, hey, the data has been received. Now I am ready to send new data. So this is a very tight system. And if you don't have a feedback acknowledgement or a proper mechanism in place, you have any false data going into from one clock domain to another, or you can have actually missed data because of metastability, you're not able to capture it. Some sample CDC failures for academic purposes. So here is in the first case, we have an unintended driver. There is an intended driver, which is properly protected by the control here, but there is a one on the red, which is unintended driver. So if you bypass this and if it thankfully gets the same value as the intended driver, there's no problem, okay? Because there is no metastability causing it the RX. But if it happens to be a different value or interacts with other signals on the path and actually changes the functionality, then you have a problem, right? You can catch this very nicely with a static tool. And on the right side, you have the same thing with a CDC interface, but without a feedback. So what that means, data is going into the receiving domain, but nobody is telling the transmit domain that I have received it. So there's no acknowledgement. When you have no acknowledgement, there is no shortage of data to be sent. It keeps sending data, and there's no way to know whether the data got received or not, right? This is a very classic problem. It used to happen a lot in the early stages. Now people have become aware of this, and people don't deploy the right methodology to make sure they don't have it. And similarly, in the below, there is a feedback, okay, but you actually take a feedback at the wrong location. So your data is getting transmitted in the next cycle to the receiver, but in the current cycle, you are giving the feedback back to the control, which means the controls will think, oh, my data has been received, so I'm going to send new data. Well, then you will run into data loss problems, right? So there's a various classes of problems. I mean, there's a lot of depth here that goes behind the scenes. I'm simplifying it. Every one of this, okay, is a real problem that we find, day to day in the field, and people have to fix this. If they don't sign off on this, you cannot really tape your chip out. And here is an interesting case. I don't want to go into the details, but just to tell you that when clocks change dynamically, okay, there's a clock 1 and clock 2 which are asynchronous to each other, and there's unconstrained select. As the clock toggles, okay, some paths become CDC paths, some paths become synchronous paths, okay? And there is no way you can know this ahead of time, through simulation or formal or even CDC. You really need some special analysis of the design and special specifications to be able to find out that, oh, there is actually a situation where transmit from block M to block O is asynchronous, which means I have to protect against it, right? And the complication behind this is, when the IP vendors send their IP, there is all parameters, okay, which can be configured. If you don't set the right configuration for your block M or block O or N or P, then you are not, synthesizing your hardware with respect to CDC correctly. Then you can run into a problem. Here are a couple of examples I wanted to show how deeper the problem is. So if you look at the top two, there is a two synchronizers here, from going from transmit to receive domain, and they go into a really critical control FSM. Okay, everything is good from the picture. There's no problem, right? Except if the data that's being sent from the transmit domains, if they are correlated to each other. Okay. And what happens when the data goes from clock domain 1 to clock domain 2, and it goes through a synchronizer, you lose coherency, or you lose the temporal correlation between the two elements here. When you lose the temporal correlation, your control FSM will generate something that looks nice, but even a slight shift in the timing, okay, of the received signal, then your operations will fail. For example, in this case is from a real use case where, based on the FSM output, there was a read operation happening, but read operation failed in this case because of metastability. There was a slight delay in the receiving waveform. Okay, and these kind of situations again cannot be detected using traditional methods. You really need dedicated software tools to go through it. And below is another interesting case we see. You have a fast clock in the transmit and then a slow clock in the receive. Okay, you need to make sure the fast clock pulse is long enough. If it is not long enough and it keeps sending the pulses, but the receive did not receive it, okay, then you are actually losing the control edge. So when you lose the control edge, then what goes out of receive is a big question mark here, because you don't know what's happening in the rest of the design. Along CDC, there's something that has emerged in the past called in the recent past called RDC, which is reset domain crossings. So what is RDC? Is a reset influences a set of sequential elements in the design for initialization. Those set of signals are called reset domain. Okay, so if you look at a power on reset, it influences a lot. That is one domain. Then if it's a cold reset, it could be influencing a smaller piece. If it's a software reset, it could be influencing even a smaller piece, and so on. But what happens is these are all talking to each other, right? In the example here, there is a simple flip-flop in a reset 1 domain interacting with a flip-flop in reset 2 domain. Okay, suppose when reset 1 asserts, okay, then the flip-flop 1 goes to 0 and it goes into the D input of the next flop. Now what happens to this next flop? If that flop is also asserted by reset 2, no problem, because that flop is asserted to 0. But suppose reset 2 is in a deassert state, okay, and both flops are in clock 1, right? And at the capture edge of the clock, you will capture this data. Okay, from the picture it looks great, but guess what? This whole path is actually untimed, because you cannot time these in static timing analysis. There are literally billions of such paths in the design, right? And there's no practical way to time these. Or even if you want to time these, you will either overtime them or undertime them. There is no, because this reset could be coming from somewhere else in the chip. So this is a very interesting problem. And what we have seen is actually this leads to yield losses in the chip. People scratching their head after silicon failure and says, what's going on? I have no idea. What is this problem? Until this problem surfaced, 3-4 years back, nobody knew actually what this problem is. Now, there's a full industry behind it, trying to get this. So CDC is typically a local problem, but it's a catastrophic problem. If there is a failure, it's a failure. Your chip is, doesn't work. RDC, the frequency of a failure is very high because the resets are everywhere in the design. But it doesn't cause as much of a catastrophic problem, but it does cause yield issues. Sometimes your chip may, if you manufacture 100 chips, 70 of them will work, 30 don't work, right? And so on. And here is something interesting that enables static again, which is design glitches, right? Most of you might be familiar with the static hazard and dynamic hazard, up, rise, down, and down, rise, up, and so on. These are very common in design, right? If you look at videos of how glitches can happen in real-time videos on the chip, I've seen one at Intel. There's actually lighting that happens, when the glitch comes. Okay. Most of these glitches are safe because why? You time the path. So the glitches, even though there's a glitch that happens in the hardware, it settles down before it gets captured. Okay. But glitches are very problematic along critical portions of the design, clock trees, asynchronous resets, test control, CDC synchronizers, isolation, and so on. So I want to give a simple example here of a clock mux here, where you have A and B both at 0, 0, and then your control select is changing to select one or the other now, right? And it goes rising, and here you go rising and you go falling, and at the AND gate you get the temporary glitch, okay? And temporary glitch means what? Your mux is supposed to be, the inputs of the mux are actually stable at 0, A is 0 and B is 0, right? No matter what the control is, it should be output should be a 0. But because of the transition path delay in the circuit, you will get a glitch. And if it happens to be on a critical path or untimed path, then this glitch can actually cause catastrophe in the design, which you will not know again through any other mechanism. So here is a couple of examples that you can see on a clock path, typically on the test clock, which goes around everywhere for DFT purposes. It fans out, then reconverges, right? You want to make sure there's no reconvergence on the, there's no glitch on the reconvergence point. Similarly, you have multiple clocks going in through a mux, could be a mux, could be a glitch-free logic, or could be ICGC and so on. You want to protect your output against glitches. And here you have a asynchronous reset. And, there could be, again, the asynchronous reset. So reset for all practical purposes is a data signal. It's not a clock signal, it's a data signal, but it's a special data signal. So there could be all kinds of reconvergence happening in resets because you want to initialize your chip as efficiently as possible. And when you do the over optimization in your design, that's when you get all these glitches. And similarly, on the right side, you have a glitch from different sources. Okay, so assuming static works great and so on, okay, there is still limitations of static. Why? You cannot go and apply the static to your 16 billion transistors all at once. It's just too many checks and it'll just explode, right? One of the practical aspects here is you want to avoid repeating the verification targets, okay? So if you go back to our picture and from the beginning, you have standard functional components, which are functionally verified, and it's your library. Then you go to your IP, you verify your IP, and whatever you verified in your IP, you don't want to re-verify again in the block run, right? And same thing with the block run, whatever you verified, you don't want to re-verify in the chiplet, and so on. In fact, most people don't even run at SoC. They may stop at chiplet because there's very little to be verified. At the SoC, it's purely connections. So the golden rules of a hierarchical flow is that your top hierarchical run should not miss a violation, okay? Because that's the whole point of static. You are trying to sign off on a particular aspect of the design problem, and you don't want to miss it, okay? The second golden rule is that you want to identify conflicts in constraints or configuration between the IP. So a simple example here, in the IP level, suppose there are two clocks which are actually verified as synchronous. But if you go to the block level run, the designer is thinking that they are actually asynchronous and he's doing the verification. But then IP owner already said they are synchronous. So which one is correct, right? Usually the upper level guy is correct because he knows the design operation from a higher view than the lower level person. So then, somebody has to go and talk to the guy and says, okay, this is not the right setup. Now we got to rerun, correct it, and rerun, and so on. So there are a lot of considerations in a hierarchical flow. You have to define your partitions. You have to define your constraints flow. You have to decide who owns what, right? Who owns this constraint? Who owns the this sort of a methodology? Is it the block ownership or a top ownership, and so on? There's a good bit of education that is needed, and this education actually is becoming very critical because there are several verification teams and several IPs which are using different tools, different methodologies. But end of the day, all of these have to perform in a single chip. Okay. I just want to give a simple example of a hierarchy here. So in a CDC, for example, you have a transmitter in one block and a receiver in another block. Okay. However, if you go in a hierarchical flow, you are not running all of this together, right? You're running one block first, another block first. When you run this block, the tool thinks, oh, you have an unprotected CDC crossing here, but actually it's not unprotected because when it is instantiated in a bigger chip, it is actually having a protection from another block. This is a very common scenario that happens in real life, and your methodology has to be aware of it and be able to specify constraints and configuration at the level. Similarly, here is a case where you have a data path. Both the transmitters are in the sending block, right? The receivers are in the receiving block. So how do you know whom the data is being sent in the block one when you run it hierarchically? And how do you know block two that you are actually receiving data from a CDC signal? So over a period of time, the methodologies have sort of developed, and they continue to develop because this is just the beginning. We are at a stage where, without hierarchical flow, we may not be able to get to the verification state. Okay. And last one, what we see as a trend is what we call continuous integration. This is actually a term used from a software world. So as your software code keeps changing, okay, in C, C++, Java, whatever it is, you want to trigger a set of compilation rules that pass so that every check-in of your code is verified. Okay. Now the same thing has sort of started slowly trickling into the hardware domain, where throughout the process of ASIC, your RTL keeps changing, and versions after versions after versions, designers keep checking their files. How do you know where a bug got introduced? Okay, you wouldn't know that. So by having enough compute power, you are actually able to trigger a set of things that can verify the check-in, each check-in, through a series of steps. I just gave a simple series of steps here. You can do linting, you can do formal linting, and then CDC, you can do RDC, you can do DFT, low power, and so on and so forth. Okay. So this has become, we already see the industry trend working towards this, and very soon, it may just be the realm. Okay, that leads to my summary here. Verification has, enormous potential because, in fact, some of the highest paid people in the industry are validation engineers. Without validation, there's no chip going out. Okay. Static sign-off continues to emerge as a practical alternative. Shift left methodology is the key, and you need to have a robust hierarchical flow. Okay, and continuous integration is happening. A couple of things that we see, there's a lot of uneducation in the field because mostly, there's a lot of emerging startups, designers, who haven't done any RTL design before, or RTL tip chip out before. they need to be educated, and as an industry, we are also working, through that process. You have to align your verification methodologies with the tools out there, and similarly, the right set of tool flow has to be incorporated in your design house. Okay. Couple of things where more work to be done in the space. Debug is not so natural, because when there is a problem, how do you know where the issue is? Okay. There needs to be more work to be done there, and interoperability between various EDA tools. It's not like IEEE standard. It has to be like an industry consortium to come together and work it out. We don't see that happening much due to the fierce competition. And finally, can AI ML be applied to verification with 100% safety? Okay, this is something we keep thinking about. What can we use AI ML? And so far, nothing. Why? Because verification needs 100% guarantee, and if you start to rely on a prediction model, obviously even the prediction is 99.9% correct, you're losing out on the 0.01%. So that's the challenge, but I'm sure people are working to it. There is a research to be done in the application of AI ML into our field. Okay, that's all. Thank you so much for your time today. Once again, thanks to VNR. If you have any questions, I'll be happy to answer.
Hi, sir. This is Vinay. Sir, I'm currently interning in an EDA company, and there are a lot of questions regarding recession and recruitment. They're stopping recruitment. So after this graduation, we are getting roles of like RTL and PDK engineers. So we would like to hear from your word, how good is it to start a career in this recession time as an EDA engineer in RTL and PDK engineer?
Actually, good question. So, I mean, maybe I'm not the right expert to answer it, but my view and what we see in our field, okay, recession is not so much of a problem for EDA industry. Okay, first reason is that EDA, so semiconductors have their ups and downs. Okay, semiconductors. So, for example, because of the pandemic, semiconductor went, 10%, 20% growth rate from 2020 to 2021 and 21 to 22. But next year, 23, semiconductor is going to go down 4%. Okay. That is because of the macroeconomic trends. And you can call it recession, but it's not really recession that's affecting semiconductor. It's really the oversupply of the parts that they have built through the last 2 years. And the demand, there's enough availability. So automatically, your new demand goes down next year. Okay. By 24, it is stable, and 25, we expect it to pick back. Okay. EDA industry is typically following the semiconductor industry, but very little. Okay. Because EDA is hardly 3 to 5% of the semiconductor industry. We are not so concerned about recession. In fact, at least I can speak from my view here. I can't speak for everybody else. There's always opportunities. There is always new problems to be solved, especially in the verification space. RTL design activity is a little slowing down through next year, but it will pick back up again in 24. So if you're starting your career, I do not think this is a problem at all. In fact, most of the programmers and engineers are going towards AI ML applications of software and so on. There will be very few people in EDA because EDA has the confluence of both the hardware and software. So it's a very key talent, key industry to be in. Okay.
Thank you, sir.
Thank you.
Thank you, sir. Thank you, sir, for your inspiring insights and your Great, sir. A few of your topics which I felt interesting and I had a note on semiconductor revenues and modern ASIC and SOC flow, established methodologies, what is static sign-off, RTL linting, simple auto format failures, resetability and XProp issues, metastability changing functionality, handshake sign-off hierarchy, and continuous integration, which was your last topic, sir. So
That's correct.
thanks a lot, sir. I think all our participants here who are live and as well as online have had a clear view on your topic. So we thank you once again. Thank you, sir.